So far we've looked at several types of functions. We kind of started our study by defining a function, and since then we've looked at linear functions, we looked at quadratic functions. We then learned that both of those are types of polynomial functions. We are now moving on to a different type of function called a rational function. A rational function is a ratio of polynomials. Rational ratio. So ratio is a fraction of polynomials. So we need to find the domain of rational functions. We need to find asymptotes, both vertical and horizontal asymptotes. We're going to talk about transformations of rational functions. And then we're going to pull all the information together to graph rational functions. Let's take a look here. I already gave you the definition of a rational function. It's a quotient or a ratio of polynomials. I gave you a few examples of graphs here of rational functions. This is sort of the standard rational function, 1 over x. It's the most basic of rational functions. Here we have 1 over x minus 2 quantity squared. And this third picture is a little bit more complicated. You can see those. We're going to refer back to these graphs a few times, so we'll come back to them when we get into more discussion. Domain of a rational function. We've talked about domain a little bit. Remember that domain is what possible values x can take on. What can x be? Any values that make the denominator 0 must be excluded from the domain, right? So in essence, we are going to take the denominator, whatever it is, remember it's a polynomial, and set it equal to 0 and say it can't equal 0. In this case, this is a nice linear function in the denominator, so x cannot be 2/3. That means our domain is negative infinity to 2/3 union 2/3 to infinity. So everything less than 2/3 can be included. Everything greater than 2/3 can be included. Just 2/3 itself cannot be, because it makes the denominator 0. The numerator is irrelevant to finding the domain of this function. It doesn't matter what the numerator is. The problem with rational functions, because they're polynomials in the numerator and denominator, is when the denominator is 0. We just spent an entire couple of videos trying to find zeros of polynomials, right? So we should be able to find and solve any domain question for rational functions, because we should be able to use our techniques that we just saw, even if the degree of the denominator is bigger than 2, this quadratic. We can use our techniques from the last couple of videos to solve if you have a bigger degreed denominator. This one is not, it's just a quadratic, so you can use whatever techniques to solve where it's equal to 0. Throw those points out. This one, I think, oh no, it's not. Oh wait, yeah, I think we can factor this. You can use the quadratic formula. If not, 3x and x will give you the 3x squared. If I put a 3 here and a 1 here, make the 3 positive and the 1 negative, I get 9x minus 1x would give me the positive 8x, and then the minus 3. So that does work. If you don't see that, how to factor that, that's okay. Use the quadratic formula. Set the factors equal to 0 in this case, because we did factor it. X equals negative 3, x equals 1/3 when you add the 1 and divide by 3. And notice x cannot equal those things, right? Because that will make the denominator, either of those numbers will make the denominator 0. In interval notation, my domain will be negative infinity to the negative 3 comes first, so exclude that. Then I need to get between negative 3 and 1/3. then I need to get bigger than 1/3. That's my domain of that function. So that's all you're doing, setting the denominator equal to 0 and solving. Let's talk about vertical asymptotes. The vertical line x equals a, remember that is the equation of a vertical line where a is a constant, is a vertical asymptote of a function f if the graph of f of x increases or decreases without bound as x approaches a. So we're saying as x gets closer and closer and closer to some number, if the graph of f of x, so you're kind of talking about y values, increasing or decreasing without bound, meaning y is going up to infinity or down to negative infinity. Let's go up. It says in these graphs above, let's break this into A, B, and C. I don't think I actually labeled those that up there, but let's go back up here. Vertical asymptote is a vertical line that the function gets closer and closer and closer to and goes down to negative infinity for y values or up to positive infinity. We seem to have that here in this picture. So that vertical line is x equals 0. Let's write that down. X equals 0. Let's go back up for part B here. So I'm calling this A, this B, and this C, just for reference later. Here we seem to have a vertical asymptote here that the function gets closer and closer and closer to, but goes up to infinity. That seems to be at x equals 2. And in C, we seem to kind of have that picture here where it goes up to positive infinity from the right side, down to negative infinity from the left side. And same thing here. Notice these red curves get closer and closer to those asymptotes going down to negative infinity or up to positive infinity. That appears to be at, I gotta look at the scale here. This is 10, so each of these marks is by 2. So this one is x equals 4. And this one is x equals negative 2. So where we have asymptotes there. I put a little note here. We typically draw asymptotes as dashed lines because they're not actually part of the graph of the function, but it's helpful to see them in there as dashed lines so we know the function is getting closer and closer to that. If we look at a graph, it's usually pretty easy to identify a vertical asymptote, but what if you're looking at the function? So here we are talking about finding vertical asymptotes from the equation of the function if you're given it. We know a rational function is a polynomial over a polynomial. So here we're saying p of x is a polynomial, q of x is a polynomial. It will have a vertical asymptote, y equals c, no, that should be an x. Vertical lines are x equals a number. For any value c where q of c is equal to 0, but p of c is not. So here's the idea. If the denominator is 0, but the numerator is not. So that's what we're talking about here. You get a vertical asymptote if you have non-zero number over 0 when you plug c in. Okay? Let's go ahead and take a look. We had asymptotes, vertical asymptotes at x equals 0, x equals 2, x equals negative 2, and 4. Let's come up here and look at these equations. This first one, x equals 0, is what we had for our vertical asymptote. If you notice, the denominator is 0 here. if I were to plug in x equals 0, I would get 1 over 0. That is a non-zero number over a 0. That is an asymptote. Here, I had x equals 2 is my asymptote. If I plug in x equals 2 in this equation, I get 1 over 0. 0 in the denominator, non-zero in the numerator. Last picture, x equals -2 and x equals 4. Let's do the -2 first. When x equals -2, I get what? 2 times 4 is 8 minus 14. I'd get -6 over, oh, I'm going to get 0 because I'm going to have 0 times -6 in the denominator. So I have -6 over 0 when I plug in -2. That is an asymptote. 4, plugging in 4, I get 32 minus 14 is what, 18 over, if I plug in 4, I'm going to get 6 times 0. So I'm going to get 0 in the denominator. All of these I have a non-zero over 0. Let's go back to our note here. Your best approach is to factor and simplify the function to see if you can simplify it away. Because if you can simplify it away, it's not going to be an asymptote in the denominator. Let's take a look at what I mean here. The denominator here factors into x minus 3 times x plus 3. You are going to have a vertical asymptote when x equals 3 and when x equals -3. Because those are values that make the denominator 0. When you plug them into the numerator, you get 5 from this one, and you get -1. Either way, you have non-zero over 0. Those are both vertical asymptotes. Let's take a look at this one. I have x plus 2 over x. Let's see. I need two numbers that multiply to give me 8. -8 that add up to -2. It is x plus 2 over x minus 4 times x plus 2. You might be tempted to say that x equals 4 and x equals -2 are both vertical asymptotes because they both make the denominator 0. But what happens here is that these factors can simplify away. That means this is not a vertical asymptote because x equals 4 is the only thing that isn't removable from the function. Sometimes we will say this is 1 over x minus equal to 1 over x minus 4. I don't like saying that because they're not truly equal because they have different domains. Because x still can't equal -2. Yeah, x cannot equal -2. It's just not a vertical asymptote here. So that's why it's a little tricky to me to say these are equal. But let's take a look at this guy. If we were to simplify this, let's factor out an x squared. That gives me x minus 4. That tells me x equals 0 is going to cause a problem in the denominator. X equals 4 is going to cause a problem in the denominator. Well, if I plug in 0, I get 0 over 0, which you might be tempted to say is not a vertical asymptote, but sometimes you can get a vertical asymptote when it's 0 over 0. Anytime you have non-zero over 0, when you plug a number in, that is a vertical asymptote. If you get 0 over 0, sometimes it's a vertical asymptote, sometimes it's not. That's why I say the best approach is to say, let's try to simplify this. And what can I simplify away? That would leave me 1 over, I still have 1x down here. And so both of these are still vertical asymptotes because I cannot get rid of that second x in the denominator. It is still causing a problem in my denominator after I simplify as much as I can. So both of these are vertical asymptotes. Up here, this one is not a vertical asymptote, only this one is a vertical asymptote. Okay, that's how we look at our vertical asymptotes. Let's talk a little bit about horizontal asymptotes while we're talking about asymptotes. The horizontal line y equals b is a horizontal asymptote of a function f if the graph of f of x approaches b as x increases or decreases without bound. So now we are talking about a horizontal line that the function will approach as x gets really, really big. So as x goes to infinity, or x decreases, talks about x going to negative infinity. So you're looking at the right end of the graph when you're talking about x going to infinity, and the left end of the graph when you're talking about x going to negative infinity. Let's go back to our graphs here, A, B, and C, and see if we have any horizontal asymptotes here. Well, as x gets really, really, really big, so we're tracing along the graph here, does it appear to be approaching a horizontal line? And the answer is, yeah, it appears to be approaching this horizontal line y equals 0. Same thing going this way along the graph. It appears to be approaching the x-axis, which is the line y equals 0. In our second picture here, we have a similar situation. The graph here traces along and approaches that x-axis, which is the line y equals 0. So these two seem to me to both have horizontal asymptotes of y equals 0. As you go forever and ever and ever to the right and to the left, does it approach a horizontal line? And they can be different to the right and to the left. They do not have to be the same. Here my graph seems to be approaching this line and the same one on this side. So we seem to have a horizontal asymptote here at y equals, that appears to be 2, right? Because remember the scale on this one is by 2's. Those are our horizontal asymptotes from the picture. Horizontal lines are y equals a number. Now let's talk about how we find those. If you are trying to find a horizontal asymptote, you want to compare the degree of the numerator with the degree of the denominator. We are focusing on this degree and this degree. Let's go back up here for a second to these pictures. In this case, the degree of my numerator is 0. And the degree of the denominator is 1. When you have just a constant, it's like having x to the 0 power, because x to the 0 power is 1. So the degree of a constant is 1. The degree of just x is 1. The degree of a constant is 0. The degree of just x is 1 because you have x to the first power there. Here, my degree is 0. Here my degree is 2. If I multiplied that out, I'd have an x squared. Here my degree is 2 of the numerator, and the degree of the denominator is also 2. Okay, so it appears in these first two examples, if my degree of my numerator is smaller than the denominator, that my asymptote, horizontal asymptote, is y equals 0. And that is true. That is what this first statement says here. if n is less than m, meaning the degree of the numerator is less than the degree of the denominator, the x-axis is the horizontal asymptote. In calculus, we talk a lot more about why that is, but just to give you a general idea, the denominator sort of overpowers the numerator because you've got that higher degree. So you get a big number in the denominator compared to the numerator. So if you have a small number over a big number, that gets closer and closer and closer to 0. And that's why we get this y equals 0. If the degrees are the same, that was the scenario in part C up here, right? We said the degrees were both 2. Our statement says that the horizontal asymptote is the ratio of the leading coefficients. If I were to multiply this out, I'd have x squared minus 2x minus 8. My leading coefficient in the numerator is 2. Down here it's 1. So my asymptote is 2 over 1. And that's what we got. Y equals 2. That's what this is saying. A sub n over b sub n, that is looking at this ratio of these leading coefficients. If the degree of the numerator is bigger than the degree of the denominator, there are no horizontal asymptotes. I decided we are not going to talk about slant asymptotes. I don't think it adds enough value that we are going to spend the time on it. So I'm going to go ahead and skip that in the lecture. Let's talk about finding these horizontal asymptotes. In this case, we need to compare the degree of the numerator which is 3, with the degree of the denominator, which is also 3. Those are the same. And if they're the same, we're in scenario B up there. Our horizontal asymptote is the ratio of the leading coefficients, which would be 2 over 4, which we would simplify to y equals 1/2, would be the horizontal asymptote of this function. Here, my degree of my numerator is 5. Make sure you're looking at the biggest number there. If they're not in descending order, you may need to make that adjustment. But here we're looking at 5 compared to 3. This is bigger. That is scenario C up here, where the degree of the numerator is bigger. So there is no horizontal asymptote. No ha. All right, last one. Degree of the numerator here is 2. The degree of the denominator is 3. Now the degree of the denominator is bigger, which is always going to leave you the x-axis, y equals 0, as a horizontal asymptote. We talked about vertical asymptotes, we talked about horizontal asymptotes, we talked about the domain of the function. It's really interesting to note that the domain and the horizontal asymptotes correlate a little bit. There could be places in the domain that do not work, that are not part of the domain, that are not vertical asymptotes. But any vertical asymptote is not part of the domain. The function is not defined there because it always gives 0 in the denominator. So it's interesting to think about how those relate. We are going to use this information that we have so far to graph functions, rational functions, in our next video.